Lesson 14, unless I change the number. In this lesson we're going to talk about sort algorithm. Well, I will tell you, don't plan to watch this video while you're half asleep in the bed at 2x speed, because you won't understand anything. Probably you'll have to stop it several times, slowly rewatch, and especially take now a piece of paper, a pencil and an eraser, and you will have to do manually all the examples that I mentioned. Will have to do, otherwise you don't understand the sorting algorithm. So, this is the warning. Probably you have already written a sorting algorithm because I asked in a previous exercise. Well, there are thousands of possible sorting algorithms. The one that people usually do whenever you have to sort, especially a small list, is the following. You go through the list, find the largest or the smallest, it doesn't matter. For example, the smallest value. Okay, pick it out and put it in another list. Then go to the list, go to what remains of the list, find the smallest, pick it out and put it in a list. Go to the list, find the smallest, pick it out and put it in a list. So, this is the basic strategy. It's a strategy which is pretty efficient whenever the list is short. Let's see, however, what is the complexity of this strategy. You have to go through a list completely one time, so n comparisons, or n additions if you go with a while loop, for example. Okay. Then you have to go through a list which is a little shorter, so first n, the shorter n minus 1, because you have already removed an element. Then you have to go through a list which is n minus 2, n minus 3, and so on. So you have to go through a list continuously, and this list is getting shorter and shorter and shorter and shorter. So at the end, this is the complexity. Measure in terms of comparisons, or if you use a while loops, you can measure it in terms of additions. Okay, what is this sum? Well, there is a famous mathematical calculation, it's also easy to show that it's true, which tells you that this sum is n by n plus 1 divided by 2. Okay. As usual, for complexity, the exact formula is not important. The important thing is that it depends on the square of n. The square of n, well, not bad, but the square of n is pretty tough, because if your list is 100 elements long, it means that you will have to do 10,000 comparisons, approximately. It's not 10,000, it's 10,000 divided by 2. Okay, if your list is 1 million elements, it means that you have to do 1 million by 1 million, which is 1 trillion comparisons, which is really too much. So a growth of n squared is not the best one. Moreover, this algorithm has always the same performance. So it doesn't matter whether you are in the worst case or in the best case, even in the average case. This algorithm does always n by n plus 1 divided by 2 comparisons. So even if your list is already sorted, this algorithm goes through and does always this amount of comparisons. We'll see here in this lesson two different algorithms. There are several algorithms, two different algorithms. Among the most famous ones, the bubble sort is the most famous easy algorithm. It's not very performant, however. And the famous merge sort, which is probably the most famous sorting algorithm, which is pretty performant. Okay, let's go bubble sort. So now take a breath, relax. Okay, bubble sort concept is the following. Have you ever seen air bubbles in water? Whenever you have a air bubble in water, the air bubble tends to go up. It goes up at a speed which depends on the size. So if you have two bubbles, the larger one, goes up faster. Okay? So if you have several bubbles, the largest one arrives first at the top, then the second largest one arrives, and so on. So the water bubbles naturally, slowly, one second after second, put themselves in an automatic order. Well, this is more or less the concept of bubble sort. Okay? The concept is that we will try to push the big elements on the right and leave automatically the small elements on the left. So imagine a list like this one. We take a small list so we don't stay here forever. Okay. We will go through the list. Okay. and compare each element with the next one. I will zoom so you see better. Each element with the next one. Okay. If they are already small, large, that's fine. If they are large, small, we switch them. So 4 with 7. 4 is smaller than 7, fine. Go on. 7 with 2. Okay. 7 is larger than 2, so I switch them. And I get 4 here. And obtain 4, 2, 7, 5, 1. Okay, then I go on, I compare 7 with 5. Okay, 7 is larger than 5, so I switch them. 4, 2, 5, 7, 1. Then I go on, I compare 7 with 1. 7 is larger than 1, so I switch them. 1, 7. Okay. Then I'm over. I don't compare 7 with something outside the list. Please remember this in the algorithm. If you do it, so if you compare also the last one, you will get index out of bounds error. Okay. At this point, so after the first pass, you can see that the largest element is automatically on the right. The rest are still in disorder, but you're sure that the largest element is automatically on the right. It means that now we do a second pass, and we won't consider the last element, because that's automatically the biggest one. So we will do a second pass only on the first 4 elements. Okay, here are the first 4 elements. We do a second pass. So 4 and 2. 4 is larger, so we switch them. 2, 4, 5, 1. 4 and 5. These are okay, so we leave them. So we leave them. Now 5 and 1. 5 is larger, so we switch them. Okay, and that's it. We don't compare 5 with 7. It's not necessary, even though we could, but it's not necessary to compare them. So remember that we arrive only to the second last position. Okay. Okay, after the second pass, we have the second largest element here. Now we'll do a third pass only on these elements here. So 2, 4, 1. May I scroll down? Okay. So 2, 4, 1, 5, 7. 2 with 4, they are in the right order, fine. Okay. 4 with 1, switch them. So 2, 1, 4, 5, 7. Okay. Now finish, because we had only 3 elements. Now also 4 is the right position. The only thing which remain to fix is this one. Okay, so we compare 2 with 1, we switch them, and we get 1, 2. Okay. Now the only elements which remains to compare is 1. Well, but you can't you have nothing to compare. 1, that's it. So when you arrive to have exactly 1 element remaining, that's it. You see, automatically the list has self-adjusted. So this technique of bubbles, where you push the biggest element to the right with this continuous switching, and in the meantime you also push the other elements a little bit to the right, then you push the second biggest element to the right, is called bubble sort. Okay, let's build the code. First we have to build a procedure which switches the elements, because it's something which we do frequently. So def switch. So we have a list and we have to switch A with B. So this procedure switches A with B in L. So we take advantage of Python, which lets us do something as follows, which will be strictly forbidden in several other programming languages. Okay. Several other programming languages will have to write temp equal LA, LB equal LA equal LB, and then LB equal temp. So a crazy thing. This in a single step, Python lets you switch them. Okay, this procedure doesn't return anything, so we don't return, because it simply modifies the elements of L. It can modify, because when you use the address like this, you modify also the external objects. Okay, that's it. If you want to test, but I perfectly trust that it works. Okay, and now we define bubble sort. Okay, however, writing the entire algorithm immediately, it's pretty complex. Let's write just the first pass. Define bubble sort first pass. Okay, we have a list. Okay. So what do? We will probably use a while loop. Okay. We compare each element with the next one if L of I is larger than the next one. In this case, we have to switch them. Switch L, we switch I with I plus 1. Okay, that's it. I think we don't have to do anything else. Okay, we just return L, because in this way I can print it. Print, let's copy the name of the which elements do we have? This one. 47251. 47251. Oop. Nothing happens. There is oops. As usual, I have forgotten I equal I plus 1. There is an error now. What's the problem? Okay. Let's see why there is an error. Whenever it stacks with an error, don't forget that you can still use you have still the variable. So if you do print I, name I is not defined, because it was inside. Oops, we have the variables but not all of them. Okay, so forget. Where is the error? Here. See, and it's index out of bounds. Well, the only index which here can goes out of bounds is this one. Why does it go out of bound? Well, it goes out of bound because I am taking into consideration also the last element. So element at length n minus 1. And when I compare it with plus 1, it goes. So let's just. Okay, here I will print whatever I'm considering. So I'm considering element 0, 1, 2, 3, 4. When I consider element 4, which is this one, well, I compare it with element 5, which doesn't exist. That's why here I told you, pay attention, because don't go beyond, so don't compare this one with something else. Okay, 0, 1, 2, 3, 4, and here, this is the first pass only. So first pass, I put the 4 here. Let's see whether it corresponds to what we did manually. 4, 2, 5, 1, 7. Yes, exactly. So this is the first pass. Let's take everything and build the bubble sort completely. Okay. Okay, in order to build the bubble sort completely, unfortunately I have to insert another while loop, because I need this thing here. At the beginning is ln of L minus 1, but then, as you can see here, it starts to get on the left, so to decrease. So I need to have a sort of, let's call it end, or finish, because end usually it's a reserved keyword. Then the minus 1. So I go up to finish. Okay. And wait, I indent everything, and I build a while loop, while finish, until finish is larger than 0, because when finish is exactly 0, I think I have to stop, or larger than 1. Let me think. I arrive up to finish is exactly the last character. I think it's enough larger than 1. Let's see. Okay, so I loop here. Well, I have here to decrease finish, however. Okay, so now this one with this one sets the end of the place in which I have to check. So first up to here, then up to here, then up to here, then up to here, up to here, up to here. up to here, no, because when I arrive having only one element, I stop. Okay, finish is here. You go on until finish is larger than 1 or larger than 0. No, larger than 0. When finish is exactly 0, I have to stop. Well, okay, let's intermediate. I also print finish. Finish, comma, and this one is instead this is a good for debugging, so you see continuously what are your variables. Let's try. I'm not sure whether it works. So finish at 4, I 0, 1, 2, 3, finish at 3, finish at 2, finish at 1. Let me see here. Print I compare, comma I plus 1. This is better information. So I compare I with I plus 1. So it finishes 4, compare 0 with 1, 1 with 2, 2 with 3, 3 with 4, finish at 3. Okay, this one is not necessary, so I can stop when finish is larger than 1. Okay. No, I seems that I have also to go on, because, can you see? I have also to go on. Okay, I compared 0 with 1, yes, that's one I must do. Okay, so this is the bubble sort. That's it. Okay. As an exercise, you will have to not only to tell me its complexity in terms of additions. Additions are, where is it? Well, if you want, you can count also this one, but usually it's this one and this one additions. Okay? And since this is a famous algorithm and you will find its complexity everywhere, I ask you to justify it strongly using this algorithm. So you have to do it yourself, you cannot copy it from the web. Let's see the second algorithm. If you think that bubble sort is difficult, well, you will now change your mind, I'm pretty sure. Merge sort. Merge sort. Let's use the proper name as they have written. There was a parenthesis here. I've lost everything. Okay. Bubble sort. Merge sort. Where's merge sort? Okay. Merge sort is an algorithm which uses a divide and conquer strategy, sometimes called divide et impera from Latin. Okay, because it's very efficient. It was invented by John von Neumann. It's probably the most famous computer scientist. The most famous computer scientist. I'm sorry to inform you that it's neither Bill Gates nor other Apple people. It's John von Neumann without any doubts in 1945. So, beware that John von Neumann invented the algorithm without having a computer. Okay, it starts from an observation. The observation from von Neumann was that the following: if you have two lists, even large ones, okay, it's easy to join them. Let's see. I add something to my. Okay, if you have two, let's see an example. Okay, suppose for example you have the usual two lists in sorted. Suppose that we have two sorted lists. So 2, 6, 8, 9, 10, and 3, 5, 6. Okay. To merge them into a sorted common list, how do we do? Well, we keep an index of both lists, I equals 0 and b equals 0. So I equals 0, which corresponds to 2, and b equals 0, which corresponds to 3. Okay, we take the smallest one, 2, and put it into a list. Okay, and consequently increment A. Okay. New line. Okay. Now what do we do? Now we have A equal 1, which corresponds to 6, and B equal 0, which corresponds to 3. The smallest one is 3, so we take it, we put it into a list and advance B. Now we have A equal 1, which still corresponds to 6, and B equal 1, which corresponds to 5. Okay, the smallest one is 5, so we put it into a list and advance B. I will now copy because I will write the same thing over and over. Now we have A equal 1 and B equal 2, which correspond to 6. Well, the smallest one here is indifferent, is any of the 2. So we put it into a list and advance A or B. Doesn't matter. Okay, let's take B. Okay, we go on. So where B now is equal to 3, and it's over, and B is over. At this point we take the remaining part of the first list and attach it to our final list. Okay, finish. The first list, which is 6, 8, 9, 10. Okay, fine. So this is the algorithm. So it's, as you can see, it's pretty easy. Just go through the 2 lists in parallel. Every time take the smallest element and advance. Okay. Oops. Okay, this one. Okay. Let's put a title so you see it better. The title here will be where is the subtitle? Merge procedure. Oops, maybe it's not. Okay. I don't know, it's so difficult to understand. Okay, now the algorithm, because this is just how to merge 2 sorted lists, but we don't have 2 sorted lists. Imagine we have a list like this one. Okay, it's not composed made of 2 sorted lists. Well, there are some parts which are already sorted, this one with this one, and nothing else. This one with this one, but it's not generally made of 2 sorted lists. Okay, so how does the algorithm work? Well, instead of explaining with this list, I will explain with this wonderful color picture which I made myself. The algorithm, pay attention because it works exactly in the reverse way that you expect. It works as follows. Okay, you have the list, this is the original list. It's not sorted, as you can see. First, I tell you, divide and conquer. So first divides. It divides the list into 2 sublists. Okay. Don't worry, the two sublists are not sorted, okay, but if they were sorted, we would merge them. But they're not sorted. They're not sorted, no problem. We divide each of the two lists into other two lists. Can you see? Tac, 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 tac. Okay. Again, they are this couple here and this couple here are not sorted, so you can't merge them. But don't worry. We take each one of the four lists and divide them into other two lists. Tac, 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 tac. Okay. Well, are these lists sorted? Well, some of them are, because if you have a list which is made up of a single element, that list is sorted by definition. So it says only one element, so it can be. So, but this one, some of them are sorted, but some are not. So we do another step. We divide again. Tac, 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 tac. This one, tac, tac. This one does not need to divide. Tac, tac. We don't divide the list made up of one element. This one, tac, tac, tac. Now we have a lot, we have, how many? 13 lists, each one made up of one element. At this point, all these 13 lists are by definition sorted, because a list with one element is sorted. And now we can merge them. So we merge 8 with 2 using the algorithm that we've seen before, getting 2, 8. We merge 1 with 0, getting 0, 1. We merge 1 with 2, getting 1, 2. 12 remains alone, 12. We merge 7 with 11, 7, 11. 9 remains alone. We merge 9 with 8, 8, 9. We merge 10, 10. Okay. Now we go up again. We merge 2, 8 with 0, 1, 0, 1, 2, 8. We merge 1 to 12, 1, 2 with 12, 1 to 12. We merge 7, 11 with 9, 7, 9, 11. We merge 8, 9, 10, 8, 9 with 10, 8, 9, 10. Now we merge this one with this one, and this one with this one, and finally we have the two big lists which are in sorted now, and we can merge using our merge algorithm track. So it's we can call this is the divide part and this is the conquer part, or better, this is the conquer part. So divide, okay, conquer because when a list is one element only, it's by definition sorted. And then there is the merge part. So divide, conquer, merge. Okay. The most strange thing of this algorithm is that it's a sorting algorithm, but as you can see, it never sorts anything. The algorithm simply splits and merge, splits and merge. The algorithm takes benefit of the fact that a list with one element is already sorted, okay, and it can join sorted list easily. Okay. So this is how the algorithm works. It's also a strange approach because it's an approach top, down, and down, top. So top, down, and then again down, top. Okay. It may seem to do a lot of operation to you, but you will see, because you will have to check it at home, that the complexity of this algorithm is much better than the complexity of the other algorithm. Okay. Let's see how to program it. First of all, we have to write a procedure which merges two lists. Okay, because we will have to merge, for example, two lists as this one with this one, or this one with this one, or this one with this one. Okay, but not any two lists. The procedure will have to take two parts, two contiguous parts, as you can see in the example, of the list and merge those parts. So, def merge. So, take a list L. How do we define two contiguous parts? We have to define this one. So, the 7, we call it left. The 11, we call it mid. Then the 8, it's mid plus 1, we don't need it. And this one, we call it right. So it accepts 4 parameters. The first one is the list. Then left is this one, defines the beginning of the first part. So let's see. Procedure merges L left is the beginning, or better, first list goes from left to mid, included. Second list goes from mid plus 1 to right, included. Okay. So, how do we merge it? Well, exactly as I explained here. We set A and B. Here I started with A0 and B0. Here I don't start with A0 and B0. I start with A left and B mid plus 1. So where the two things start. Okay, I defined an empty list in where I will put the result. Okay, now I go through the list. While A smaller than the end, smaller or equal than mid, and B smaller or equal than right. Okay, so I will go on until A and B both are before their end. Okay, if L of A is smaller than L of B, in this case I will append L of A and I will increment A. Else I will append L of B and increment B. Okay. At this point, when we arrive here, one of the two lists is over. We don't know which one, however, so we check if A equal if A is still smaller or equal to mid, it means that it's the other one. So A still has first list still has some elements left. Okay. If this is the case, we will add the rest. So R equal R plus L of starting from element A and going up to the end of the list, which is mid plus 1 because Python wants the next one. Okay, else, in this case instead it's the second list which has some elements left. B right plus 1. Okay. 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 At this point in R we have the sorted list. Okay. And we have to overwrite. That's right. And we have to overwrite that part of L with R. Okay, so there is a part of L, so L from left to right plus 1 because it's Python will be overwritten with R. Okay, since I don't trust too much writing, I prefer to put some parentheses because you never know what happens with that colon. Okay. Let's test it because, so with L, for example, oops, 1, 4, 7, 9, 2, 4, 6, 7, 5. This is our list. So merge the list L. I start from 0 to 3, 7. So we merge, here we merge, let's see, 0, 1, 2, 3 with and leave 5 alone. Okay, there. Okay, so we merge the first 4 elements with the next 4 elements, and the 5 is untouched. This is just to test that the procedure doesn't touch elements which should not be touched. So print L, that's it. 1, 2, 4, 4, 6, 7, 7, 9, and 5 remains untouched. Very well. So I save also because I would like to keep all this precious code. Okay, now we have a procedure which merges, and you can say, well, if the procedure which merges is so complicated, well, by the way, it's not complicated, it's so complicated, I can't imagine the algorithm. Don't worry, the algorithm is easy peasy, because the algorithm, look, once you have the procedure which merges, you do automatically all this part. Okay, this part, what does the algorithm do? Splits the list in 2 parts, then splits each remaining list in 2 parts, splits each remaining list in 2 parts, splits its remaining list in 2 parts, everything until the list is made up of a single element. So the algorithm continuously calls the same routine, the same procedure. So take a list and split into parts, take a list and split into parts, take a list and split. So we can apply the algorithm recursively in this way. Def merge sort L this procedure applies merge sort to L from left to right. Clearly, the first time you call it, you must call it from 0 to len of L minus 1. From left to right included. Okay, so the first time you call it from 0 to L minus 1. It means that you merge sort the entire list. Okay, then we will apply it here. So you call it from 0 to this point here. Then we will apply it here. So from 0 to this point here, and from this one to this one. So let's see what does it do. If left is smaller than right, it means that our list has more than one element. Because if your list has only one element, you don't do anything. Okay. So what we calculate the midpoint. Maybe if I put some parentheses, it's better. Okay, and then look, merge sort. I was very surprised the first time I saw it because it's so easy. Merge sort of L from left to the midpoint included. Then merge sort of L from the midpoint plus 1 to the right. Okay. And then merge L from left to the midpoint and then right. Finish. Finish. It seems incredible, but it works. Let's see why. The first time you call this procedure, you call it with 0, and here the length of the list minus 1. Yes, minus 1 because, in Python the last element is length of the list minus 1. Okay? This is just to check that the list has more than one element. For sure it has. You calculate the point in the middle. So here, the point in the middle, which is this guy's 12, this one. Okay? And then what do? You call the subroutine again, okay, from left to mid, and from mid plus 1 to right. So you call again the subroutine on this orange list and on this gray list. What does it imply, calling the subroutine again? Calling the subroutine again implies that again you check that the subroutine has that the list has more than one element. Okay, you find the midpoint, this one. You split it into parts, and you call the subroutine again with this one and this one. On the other side, same thing. And then you call the subroutine again, you stop this procedure of continuously calling the subroutine only when all the elements have exactly one all the lists have exactly one element, because at that point you can see the if doesn't work anymore. Okay. And after you have called these two things, what you do, you join them. Okay. It means that when you call them at low level, so here, okay, you join them, you merge them. Okay. And when you call at high level, here, you wait for all the rest of the procedure to do. So it's very strange, because there is the way of reasoning, you have to suspend somehow. So you split your list in two parts, then you have to suspend your thinking and see what the rest does. The rest will do something here and something here, and then here you will have magically the two things sorted, and then you can merge them. Okay. Same thing here. You have this one. You split in two parts. Then you have to suspend everything. You have to leave the other recursive calls do whatever they want. And then here you will have the two parts magically in order, and you can merge them. So these two things seems just two easy instruction, but they call again merge sort, which will call again merge sort, which will call again merge sort, which will call again merge sort, until all the lists have a size of 1. At this point I will call merge. Okay. Then they will go back and call merge. They will go back and call merge. They will go back and call merge and call merge and call merge, etc. In order to understand what the procedure is doing, because I'm sure that it's pretty difficult, we will do some printing. Merge, sort, called, and let's write parameter. So left, right. Okay, here print, we are calling merge sort, let's write parameter, left, mid, merge sort first time, and here we are calling merge sort second time, this time mid plus 1 and right, and then we are calling merge now let's put also L every time, so we have an idea of the left, mid, right. Okay, at the end of it you will have magically your routine sorted. Okay, save. Let's see, L equal. Let's take exactly the same example as before, the big one. So 8, 2, 1, 0, 1, 2, 12, 7, 11, 9, 9, 8, 10. Merge sort L from 0 to the length of L minus 1, and then print the final result. Let's cross our finger. I save because you never know. Let's see. Merge sort called, this is the original list, from 0 to 12. Okay, fine. We are calling merge sort first time, so we are here now. Okay, the list is always the same, from 0 to 6. So this is the first merge. Okay, and then merge sort called from 0 to 6. Okay, now you have to, from 0 to 6 you have to split again. We are calling merge sort first time from 0 to 3. You may ask yourself, what is the rest from 7 to 12? Well, the rest from 7 to 12 is below, because only when all this merge sort are finished, it will start with the second one. So here, 7 to 12 here, we're calling merge sort second time. Okay, then from 0 to 3, then from 0 to 1, then from 0 to 0, and from 1 to 1. You see, at this point you have 0, 0, 1, 1, so you have the first two elements, 8 and 2. Okay, and we are calling merge this time on this thing here, from 0 to 0 and from 1 to 1, so these two things. Okay, and now we are calling merge for second time, 2 to 3, 2 to 2 and 3 to 3, and then join them together. It does exactly what indicated here. So first fixes this 2, then fixes this 2, then you will see fixing this 2. Okay, at the very end, look at the very end, you see, we are calling merge here from 0 to 6, so 0, 1, 2, 3, 4, 5, 6, okay, and from 6 plus 1, so 7 to 12. So it's merging this one with this one, so which is exactly what was indicated here. So it's very surprisingly that this is a recursive call, but while in binary search you are calling recursively one time only, here you are calling recursively 2 times the same subroutine. Okay, and it works. It opens, opens a tree of possibilities. You can see all the possible possibilities here. It's pretty a lot of things. Okay, and that's it. Goodbye. Save.